Friends, you might have heard the statements like no two students score exactly the same marks, no two machines produce identical parts, and no 2 days feel exactly alike. What do you mean by all this? We are indirectly meaning some variation associated with the problems. And that small difference is what is called variation. And the standard deviation or sample standard deviation is how we measure it statistically. From a practical perspective, imagine you measure the height of 10 people. You get different numbers, right? But how do you express how much is the spread between these numbers? And that is where the sample standard deviation comes in. It tells us how much the data vary from the average. In this video, I will explore what the sample standard deviation is, how we estimate it, and why it is one of the most important measures of variability in research and data analysis. Okay, so let us see some important estimates. Sample standard deviation is a statistical measure of data spread around their mean in a sample, not the entire population. If x1, x2, etc., xn are the sample observations, then S can be computed as square root of 1 upon n minus 1 summation xi minus x bar whole square. So where x bar is actually the sample mean. If you take the square of this, that becomes the sample variance. And sample variance, S square, is interestingly is a minimum variance unbiased estimator for the variance parameter sigma square, provided the data are normal. It has been found that this estimator is sensitive with respect to outliers and hence it is not robust. So one of the drawback of this particular estimator is that it is not robust, although it is efficient and practically used and widely used. Another estimator is we may call distance-based estimator that is computed using the formula 2. You can see that it's 1 by square root of 1 upon n times n minus 1 summation xi minus xj, also that distance can be measured here. This formula shows that the sample variance is proportional to the average of the squared interpoint distances xi minus xj, and that's why it's called distance-based estimate. And both 1 and 2 will give identical result. There will be no change even in decimal points also. And the choice between 1 and 2 is depends on the context. If you are getting the data in the natural order, probably the equation 2 will be much easier and much faster than the first one. Sample standard deviation estimates. For any random sample drawn from a distribution with finite variance, the sample variance will be unbiased estimator of sigma square, and we can prove it also theoretically. And it also follows that the sample standard deviation is a biased estimator of the underlying population standard deviation, but the bias has an analytic expression when the data are Gaussian or normal. It's given in the expression 3, and that involves a gamma function as well. So if samples are distributed normally, then for n equal to 20, the sample standard deviation has expected value 0.9869 sigma. So the bias is somewhere around 0.01. So if you increase the sample, so probably you will be able to get a slightly close to sigma. So that the bias will reduce considerably. So the more the sample, the better the approximation is going to be. So you get finally an unbiased system. Here is another estimator which is very famous. Most of the time econometricians and economists use this kind of estimators, and it's called Guinness mean difference estimator. So that's given as 2 by n into n minus 1 summation absolute difference between xi and xj. And the difference here is that the squared interpoint differences are being replaced by absolute differences. So the negative part also will be taken care of by taking absolute value instead of squaring also give you takes care of the negative part. So another way, it's very important, very powerful and very robust. The best part of this estimator is that it is robust, and that's the reason why this is considered in quantifying risk in financial applications. But unfortunately this is not very efficient. So we have now two types of estimators. Now we have robust estimators and efficient estimators. I will show you and execute through an example which estimators are going to be efficient, which are robust. Okay, here is another important estimator. This is known as mean absolute deviation estimator. So that is computed as median of the absolute differences between xi and median of xj. Okay, so you can very easily, you can manually also, it can be done. And if a large sample is drawn from a normal distribution with variance sigma square, we can see that this expected value of MAD will go to 0.6745 sigma. So there is some bias. Bias will increase. Definitely, bias can be reduced if you are looking at a big or large data set. MAD is often used to give an auxiliary estimate of scale for other more complicated scale estimators, and for large N, it's commonly scaled so that it is asymptotically unbiased for the standard deviation of sigma. That's natural. And here is a very interesting and a very useful estimator, very efficient estimator rather. So this involves some another function which within the formula, that is actually a standardized variable of xi with the m and sigma naught. So is it what is called a score estimator, that is given as square root of 1 upon n summation 1 upon zi square xi minus m whole square. So and zi is given as xi minus m by sigma naught. And m is called an auxiliary estimate of location. And sigma naught is the scale parameter that can also be assumed to be something like range or some quartile range, interquartile range or something like that, to start with an initial estimator for zi. So, interestingly, this estimator is going to be very efficient provided m is considered to be the mean. If you are considering median, definitely the estimator becomes slightly poor, but still you get a good estimate. So let's see an example. This example is based on battery lives of 40 similar cars, batteries, and you can see the data. The data follows normal, no doubt, and the estimates are given according to the formulas 1, 2, 3, 1, 2, 4, 5, 6. So 4, 3 is not considered because it's very poor estimate. So here the efficiency is compared based on 2, estimator 2. Okay, now you can see estimator 1 and 2, as I already informed, they are similar and only the calculation differs, that's all. And 4, 5, 6 are compared with respect to 2. The efficiency you can see for 4, that was one of the best estimator we have seen, the robust estimator, but slightly inefficient, 80.17%. Fifth one and sixth one. Sixth one is the most efficient, but then that may not be robust. The reason is if you consider m as mean, definitely the efficiency is very high. Median, if you consider, definitely it becomes a poor estimator. And if it is mode, suppose, because m is an auxiliary estimator, so if you consider m as the mode, definitely the efficiency will go down and it may not be robust. So there is another example. This is generated from the normal distribution with the mean mu 10 and sigma square as 9. So observations are shown here. The same table, you can see the formulas, estimates based on formula 1, 2, 4, 5 and 6 is computed. Here again, the conclusion is same. So the estimator obtained in 6, one is more. The efficiency is very high when you compare with that. Okay, now yes, interestingly, for fifth one is also giving a better than the robust estimator. So robust estimation, generally statisticians go for the efficient estimator, and for most of the cases. And if you see econometricians and economists, they may go for a robust estimator like Guinness difference estimator. Okay. So use of sample standard deviation is used in research by everyone. I'm sure that most of the academics, their students or research scholars, even faculties, they might have used standard deviation at least once in their life. So they have a lot of importance. Measure of variability, that's the best one. Okay, instead of interestingly, even against variance, people always talk about standard deviation. So how much individual observations differ from the sample mean? That's the best one is variability is this sigma. So comparing groups help assess whether two or more data sets have similar or consistent. And even very often it is used in quality control to indicate consistency or inconsistency in industrial or clinical trials data. Even sigma becomes the foundation of all statistical calculations and inferential studies like ANOVA, regression, confidence intervals, where very often we use standard errors. Okay, so standard error of mean, sigma by root n is very famous. And the model building, of course, plays a central role in statistical modeling. And it is also used for quality check. The best and very easy to check the quality of a data is see the standard deviation, compare with the one and the, that's all. So you can see the diversity on the sample. Similarly, it also have a lot of significance in research. Interpretability is the best one. Instead of, as I told you, very often you can interpret standard deviation as the absolute measurement base and rather than variance, because variance, when you say it, becomes altogether a square of the standard deviation. So it's also an indicator of reliability. So smaller standard deviation means observations are tightly clustered and research results are more consistent and reliable, and it also helps in decision making. And researchers very often use for sigma for their decision making. It's for basis of almost all hypothesis testing. You need a standard error, so automatically the value of computation of sigma comes into the reality. Comparing variability across studies, so meta analysis studies, the cross sectional studies, surveys, we also always use sigma. So that becomes the basis for even sample size calculation. We need a sigma, and that's the purpose of this presentation, because we can use sigma and as an estimator for all these kind of inferential studies. Effect size and practical significance. In psychology, medicine, and social sciences, the ratio of mean difference to standard deviation measures how meaningful results are. So in short, standard deviation is widely used in research because it is intuitive, comparable, and essential for statistical inference, and it directly influences conclusions about how reliable and significant research findings are. So I request the audience to see my book Six Sigma for Organizational Excellence, where there is a full chapter dedicated on Sigma estimator. You can have various other estimators, their computations, efficiency computation, comparisons with other existing estimators like UMV estimator, CAN estimators, etc. etc. So please have a look at that book. Okay, so keep watching my next video on the channel, Elucidation and Interpretation. Thank you very much.